Hello everyone. In this video, I'm going to be explaining some core properties of logarithms. Logarithms are very important in all of physics and mathematics, and it's very crucial to understand them and know how to apply them to be able to get a good grasp of those subjects. So let's begin. First, I want you to consider these two equations. 5 raised to x is equal to 5 and 5 raised to x is equal to 25. What are their solutions? You'll say that's easy. 5 raised to 1 is 5, so x equals 1 is the solution of the first equation, and similarly 5 squared will be 25, so x is equal to 2 is the solution over there. But what if I ask you the solutions to these equations? 5 raised to x is equal to 20 and 5 raised to x is equal to 20. You'll realize that they can't be solved with simple inspection. We may get a brief idea like the solution of 5 raised to x is equal to 20 is going to be between 1 and 2, but we can't exactly pinpoint where. So to simplify these equations, we use the logarithmic function. What is the logarithmic function? If x and b are positive real numbers such that b doesn't equal 1, then y is equal to log x to the base b is called the logarithmic function with base b. Y is called the logarithm, b is called base, and x is called argument. But what does this equation actually mean? The equation y equals log x to the base b is nothing but the same as b raised to y equals x. Both are equivalent and pretty much the same equations in different form. One is called the logarithmic form and the other exponential form. So whenever we are taking logarithm of a number with a particular base, we are basically asking the question that to what power do I raise the base to get the number inside the log? A conclusion we can also derive from this is that the exponential and logarithmic functions are basically inverse of each other. In other words, if f of x equals b raised to x, the inverse function f inverse x is equal to log x to the base b. Let's look at a few examples. If let's say we want to find log of 32 to the base 5, we are just asking that to what power must we raise the number 2 to get 32. In exponential form, that is the same as 2 raised to x equals 32. And we know that the fifth power of 2 is 32, so we get log 32 to the base 2 as 5. Another example, log of 1 divided by 1000 to the base 10. In exponential form, that's 10 to the power x equals, now 1 upon 1000 can be written as 1 upon 10 cubed, or in other words 10 raised to minus 3. So 10 raised to x equals 10 raised to minus 3. As bases are same, we can make powers equal as well, thus x equals minus 3. If you find this confusing, you can have a look at the video I made on laws of indices, which will make this a lot clearer. I'll link it down in the description. Now, the next example, log 1 to the base 5. That's same as 5 raised to x equals 1, and we know that we would have to raise 5 to the 0th power to get 1, so x equals 0. Again, we have used a property of index here, which you can check in the video. Now let's actually look at the properties of logarithms. The first one is pretty simple. Log of 1 to any base is going to be 0. That's because, let's say for example, take log 1 to the base 5. So what power would we have to raise 5 so as to get 1? There is only one possible solution there, and that's 0. Any number raised to 0 is 1. Now for these properties, or while dealing with logs in general, we need to be careful about a few things here. Like the number and base should be positive and base shouldn't be equal to 1. Why is that? Because if let's say the base is 0, then what would be value of log 5 to the base 0? What power would you raise 0 to get 5? And that's just impossible. We can never get 5 by raising 0 to something. The log would have no solution, so 0 in base isn't allowed. Same for negative numbers. What would be log of minus 4 to the base 2? That would have no solution as well, because no power of a positive number would give us a negative number. And another thing here is that base shouldn't be 1, because powers of 1 are all just 1. So we would get no solution for an equation like x is equal to log 5 to the base 1, because any power of 1 will never be equal to 5. So keeping all that in mind, let's look at the second property. Log of any number to the same base is 1. For example, log of 8 to the base 8 equals 1, which makes sense as first power of 8 would give us 8. Third property, which is an important one, it's called the power property. Log of x raised to b to the base b equals p log x to the base b. So if there is a power to the number of which we need to find log of, then we can remove that power outside and multiply it to the log. Like for example, log of 1 half raised to x to the base 1 half equals x. Here x came out and what remains is log 1 half to the base 1 half, which by using second property is going to be 1. So we get the answer x. Fourth property. This property is applicable when log is an exponent of a number and the base of that log is same as that number. So b raised to log x to the base b equals x. You can keep it in mind as the b raised to log to the base b gets cancelled out and only x remains. Same is evident in the example. That is 10 raised to log x plus 2 to the base 10 equals x plus 2. Here 10 raised to log to the base 10 gets cancelled and x plus 2 remains, which is the answer. Fifth property, very important as well, called as the product property. Log xy to the base b equals log x to the base b plus log y to the base b. So basically, the logarithm of the product equals the sum of the logarithms of the factors. For example, log 27 to the base 3. We can write 27 as 9 multiplied by 3, and using the property, we get log 9 to the base 3 plus log 3 to the base 3. Log 9 to the base 3 is just 2, and log 3 to the base 3 by property 2 is going to be 1. So 2 plus 1 gives us the answer 3. Sixth property is the quotient property. Logarithm of a quotient equals the difference of the logarithms of the numerator and denominator, exactly opposite to the product property. So we get log x upon y to the base b equals log x to the base b minus log y to the base b. For example, log 10,000 upon 100 to the base 10 can be written as log 10,000 to the base 10 minus log 100 to the base 10. Log 10,000 is just the fourth power of 10, so answer to that is 4, and minus log 100 to the base 10 is just 2, as 10 squared is equal to 100. The answer is 4 minus 2 equals 2. Now I have demonstrated it in this way to verify the property and show you that it could be solved in this way as well. The simpler method for this would be that we just divide 10,000 by 100, which will give us 100, and then log 100 to the base 10 is going to be 2. There is actually one more property which is quite important, so we'll see it separately. It's known as the change of base formula. Let a and b be positive real numbers such that a and b do not equal 1. Then for any positive real numbers x, log x to the base b equals log x to the base a divided by log b to the base a. This formula is very useful when we want the base to be different. So this way, if a question is given in a particular base and we don't know how to solve it, then we can just change the base to whatever we like to make the question easier. For example, log 80 to the base 4 can be written as log 80 to the base 10 divided by log 4 to the base 10. The values of log 80 and log 4 can be found using a calculator or a log table, and by using that we get the answer 3.161. We can also change the base to another number like e. What e is we will see soon, but the values are written from a calculator and we get the same answer, as you can see. So whatever base we change it to, the answer we will get the same. So the final conclusion is that 4 raised to 3.161 is going to be equal to 80. Now based on the basis, there are two types of logarithms. The logarithms with base 10 are called natural logarithms. They are usually simply written as y equals log x. So whenever the base isn't given in a question, we have to assume that the base is 10. And then there are natural logarithms, which are the logarithms with base e. This number e we encountered before as well. So what's e? The proper definition is that it is the limit of x plus 1 upon x raised to x as x tends to infinity. If you don't know about limits, then don't worry a lot. Just keep in mind that e is a irrational number and also a universal constant just like pi. Its numerical value being 2.718 and so on up to infinite digits. If you want to verify and understand what we have written in this equation, then you can just check the values of x plus 1 upon x raised to x by substituting any number for x. So as you keep substituting bigger and bigger numbers for x, the values keep approaching the approx value we have written here. Like in this table shown here, we have 100 substituted in x plus 1 upon x, then 1000, then 10,000, and so on. The bigger the number we substitute, the closer we get to the actual value of e. But still, it won't be exact until we reach infinity, and at that point, we will get the exact value. So, yeah, those were the basic properties of logarithms. There is more to logarithms like logarithmic function, its properties, and logarithmic inequalities. We'll cover those in a separate video later. So, for now, let's solve some solved examples based on these properties. So let's find the values of these three questions. The first one is log 4th root of 3 to the base 3. So what we are going to do here, we are going to write 4th root of 3 as 3 raised to 1 upon 4 to the base 3. And now we use the power property and take the 1 upon 4 outside, and this becomes 1 upon 4 log 3 to the base 3. Now the number and base is same, so that's just going to be 1. So we get the answer of the first question as 1 upon 4. The second question is log 0.0001 to the base 10. Log 0.0001 can just be written as 10 raised to minus 4 to the base 10. Again, we take the minus 4 outside, and this becomes minus 4 into log 10 to the base 10. Log 10 to the base 10 is 1, so the answer is minus 4. Third question is simple as well. This is log 560 to the base 2 minus log 7 to the base 2 minus log 5 to the base 2. We solve the first two terms by using the quotient property. We write this as 560 divided by 7 to the base 2 minus log 5 to the base 2. Now 560 divided by 7, that's just going to be, yes, 56 divided by 7 is 8. So this is log 80 to the base 2 minus log 5 to the base 2. Now we just divide 80 and 5. Again, base 2. 80 divided by 5 is going to be 16 to the base 2. What is 16 to the base 2? So what power do we raise 2 to get 16? So that's going to be the fourth power. So the answer to this is 4. Now similarly, let's solve some more questions. We have to write these expressions in expanded form. So we have to expand these. How do we expand them? So first of all, we use the quotient property in reverse and write this as log of xy cubed minus log of z squared to the base 3. Okay, and then we use the product rule for the first term. So this becomes log x to the base 3 plus log y cubed to the base 3 minus log z cubed to the base 3. Log x to the base 3 can be written as it is. The 3 comes outside, and this becomes log y to the 3 times log y to the base 3 minus 3 times log z to the base 3. Okay, so that's it. This is the answer. We have expanded a single expression of log. In the similar way, we have to expand the second one. How will we expand this? Again, first of all, we'll have to take the root out of the equation. For that, we will write it as raised to 1 upon 2. The 1 half will come outside, and what's remaining inside can be separated using the quotient rule, and we write it as log x to the 5 minus log yz cubed. This equals 5 can be taken outside, so this becomes 5 times log x to the base b minus log y to the base b, and then log z cubed to the base b. Okay, let's first write it as one term, and then we can multiply the negative sign in the next step. So this becomes minus log y to the base b minus 3 can be taken outside, and this becomes 3 times log z to the base b. This is the answer to the second question. The third one is simple as well. ln x. So what is ln x? Ln x is just basically log to the base e. It is called as ln. So this can be written as ln x minus ln cube root of y into z. We use the product rule in the second one. Write it in bracket and separate it in the next step. We will write this as 1 by 3 ln y. Why did we write it as 1 by 3? Because cube root of y can be written as y raised to 1 upon 3, and then we took 1 upon 3 outside the log sign. So this becomes ln x minus 1 upon 3 ln y plus ln z. This is the answer. Now let's solve some more questions and write these expressions as a single log, the opposite of what we did in the last question. So basically, we will write this as log x squared. We are doing the opposite process of what we did in the last question. Now we have to take the powers inside instead of outside, and this becomes log z cubed. Now we use the quotient rule in the first two brackets. So this becomes x squared, and y raised to 1 upon 2 can be written as root y plus log z cubed, and then using the product rule, this just becomes x square z cubed divided by under root y. This is the single expression. Remember here that the base is ungiven, so base is assumed to be 10. Okay. The next question is simple as well. We use the product property in the first two brackets. So this is going to be x plus 2 multiplied by x minus 2 minus 3 times ln x plus 5. We will take the 3 in the power of x plus 5. Now here we know a property that a minus b multiplied by a plus b is just going to be a squared minus b squared. So the first term becomes a squared, that is x squared, minus b squared, that's 2 squared, which is going to be 4, x squared minus 4, and ln x plus 5 cubed. Using the quotient property, this can be written as x squared minus 4 upon x plus 5 cube. This is the single expression for the above separated logarithms. Next question. Let's show that log a square upon bc plus log b square upon ac plus log c square upon ab equals 0. How do we do this? So just as two logarithms, the product property can easily be extended for 3 sum of logarithms. So for example, log x plus log y plus log z, this is going to be log x times y times z. So we'll do the same in this question, and we can write this as a square upon bc multiplied by b square upon ac multiplied by c square upon ab. This is the left hand side. Okay, the numerator is going to be a square b square c square divided by, there is one b here and another b here, so b multiplied by b is b squared, a c here and another c here, so c multiplied by c is c squared, and a multiplied by a is going to be a squared. So this is just going to be log a squared b squared c squared divided by a squared b squared c squared. Both of these get cancelled out, and this is just going to be log 1. Okay, so the base here is 10, and we know that log 1 to any base is equal to 0, and this is what we needed to show. Okay, now let's solve this one. Log x cube to the base y multiplied by log y raised to 4 to the base z multiplied by log z raised to 5 to the base x. So the left hand side here, what we are going to do is, first of all, we take the 3 outside. So this becomes log x to the base y multiplied by 4 log y to the base z multiplied by 5 log z to the base x. Pretty simple, we use the power property. Now 3 multiplied by 4 multiplied by 5 is just going to be, yes, 60. Now here we will use the change of base formula to write log x to the base y as log x upon log y multiplied by log y upon log z and log z upon log x. The base can be taken as anything, but we have taken the base 10 here. You can take it anything, which doesn't matter actually, because all of these are just going to get cancelled out. Log x, log y, numerator and denominator gets cancelled out, and log x log z also get cancelled out. The answer is just going to be 60, which is the right hand side. Okay, so this is how you solve the questions. Let's see some more. So here we have to solve for x. We have to find the value of x which satisfies this equation. So as the bases here are same, log x 8x minus 3 to the base x minus log 4 to the base x, we can just write this as log 8x minus 3 divided by 4 to the base x using the quotient rule. This equals 2. Now we can just use the definition of the log here. What is the definition of the log? And if log a to the base x is equal to b, then x raised to b is just going to be is equal to a. So we can write 8x minus 3 upon 4 equal to x squared. Cross multiplying, we get 8x minus 3 is equal to 4x squared. Taking all the terms on one side, we can write this as 4x squared minus 8x plus 3 equals 0. Here we get a quadratic equation which can be solved very easily. We need the multiplication as 12 and addition should be minus 8. Two numbers which have multiplication 12 and addition minus 8. So what are going to be those numbers? So pretty simple, these are going to be minus 6 and minus 2. So we write this as 4x squared minus 2x minus 6x plus 3 is equal to 0. We take the highest factor from the first two terms as common. So 2x common, in bracket remains 2x minus 1. Again, from the last two terms we take minus 2 common, which is the highest factor, and this becomes 2x minus 1 is equal to 0. Again, taking 2x minus 1 as common, this is 2x minus 1, 2x minus 2 is equal to 0, and 2x minus 1 is equal to 0, or 2x minus 2 is equal to 0. We know how to solve this. So this is just going to be x is equal to 1/2, or x is equal to 2 by 2, which is just is equal to 1. So we get two solutions for x here, 1 and 1/2. Okay, similarly, second question is also pretty simple. We can just use the definition again here. So log, and whatever is inside the log, let's write it down. So log x to the base 3 to the base 2, this is just going to be is equal to 3 raised to 1 using the definition. Now again, we will use the definition here and we will write what's inside the log, which is log x to the base 3 as 2 cubed. 2 cubed is just 8, and now x is going to be equal to 3 raised to 8. What is 3 raised to 8? We can check that easily to get the answer 6561. This is the answer to the second question. The third question is a little bit different. Here we have different bases for every term. Log x to the base 2 plus log x to the base 4 plus log x to the base 16 equals 21 upon 4. So how do we solve this one? Whenever the bases are different, we try to make the bases same. So how do we make the base same? One common theme we can observe here is that all the bases 2, 4 and 16 are going to be the powers of 2. So let's write it that way. Log x to the base 4 can be written as 2 squared plus log x to the base 16 can be written as 2 raised to 4, and this equals 21 upon 4. Now here we will have to apply a property which is similar to the product property. What is the product property? We know that log of x raised to p to the base p is going to be p times log x to the base b. Right? There is a similar property to this. If the power is not in the number, but let's say it is in the base, then the same power will come outside in the denominator. So this is going to be 1 upon p log x to the base b. So the power of base comes outside in the denominator and power inside the number comes outside in the numerator. So this can be written as log x to the base 2 plus this 2 comes outside and becomes 1/2 log x to the base 2 plus again 1 upon 4 log x to the base 2 equal to 21 upon 4. Now we just take log x to the base 2 as common. What remains inside is going to be 1, 1/2 and 1/4. This equals 21 upon 4. What's inside the bracket can be solved easily either using cross multiplication or just we can try to make them the bases same. So 1 can be written as 4 upon 4, 1 upon 2 can be written as 2 upon 4, and 1 upon 4 we will write as it is. Now as the bases inside the bracket is same, we just add the numerators and get 4 plus 2, 6 plus 1, 7 upon 4 equals 21 upon 4. This 4 and 4 get cancelled, 7 and 21 get divided. So we get log x to the base 2 equals 3, and using the definition we get x is equal to 2 cubed or x is equal to 8. This is the solution for the third question. So this is a little bit unique question. Let's solve one more like this. X plus log 1 plus 2 raised to x to the base 10 equals x times log 5 to the base 10 plus log 6 to the base 10. So how do we solve this one? So what we can observe here is that in the first term there is no logarithm, and in the rest 3 terms there is a log to the base 10. So what we have to do here, we have to bring log to the base 10 somehow in the first term as well. How will we do that? So we know that there is a number 1 which is always in multiplication with this variable x. So we can write that 1 as log 10 to the base 10 plus log 1 plus 2 raised to x to the base 10. And what we will do here is that we will write this as 5 raised to x to the base 10. We took x inside the logarithm by using the product or the power property. Okay, now we have log to the base 10 everywhere, just that now this x should be inside. So this is log 10 raised to x to the base 10 plus log 1 plus 2 raised to x to the base 10, and the right hand side will be same as it is. Now we will have to use the product property or the sum property, and we can write this as log 10 raised to x multiplied by 1 plus 2 raised to x to the base 10, and this is equal to log 6 multiplied by 5 raised to x to the base 10. Okay, sum of logs is equal to product of one log. Okay, now log to the base 10 can just be cancelled out from both the sides, and we get 10 raised to x plus 1 plus 2 raised to x is equal to 6 into 5 raised to x. We divide this equation by 5 raised to x to get 10 raised to x upon 5 raised to x multiplied by 1 plus 2 raised to x equals 6. 10 raised to x upon 5 raised to x can just be written as 10 upon 2 raised to x, as we know the property that a raised to m upon a raised to n is equal to a upon b raised to n. Okay, so This is going to be 2 raised to x. 1 plus 2 raised to x is equal to 6. Multiplying 2 raised to x in the bracket, we get 2 raised to x multiplied by 2 raised to x is going to be 2 raised to x squared is equal to 6. Now 2 raised to x we will put as another variable, let's say t, to simplify this. So this becomes t plus t squared is equal to 6, or t squared plus t minus 6 is equal to 0. We get another quadratic equation here whose solution we will have to find by finding two numbers whose multiplication is minus 6 and whose subtraction is plus 1. Which are those numbers? Plus 3 and minus 2. If we multiply them, we get minus 6, and if we subtract them or add them, we get plus 1. So this is t squared plus 3t minus 2t minus 6 is equal to 0. Or instead of doing this, we know that if alpha and beta are two roots of a quadratic equation, then x minus alpha, x minus beta is just going to be the solution. So we can write this as t minus 3 and t minus minus 2, which is t plus 2, is equal to 0. So t minus 3 equals 0 or t plus 2 equals 0. So we get t equals 3 or t equals minus 2. Now we know that t is just 2 raised to x. So we substitute it back and we get 2 raised to x is equal to 3 or 2 raised to x is equal to 2. The second equation is simple. 2 is just 2 raised to 1. Bases are same, so powers will be same as well. So x is equal to 1 is one of the solutions. And for this, now we know how to solve these type of questions. We just take logarithm. So by definition, if 2 raised to x is equal to 3, then what is x going to be? X is going to be the log of 3 to the base 2. By using the definition, we can say that this is the value of x. So that's our video on properties of logarithms. If you found anything confusing or have any doubts, comment down below. I'll try to answer them. Also, if you want any particular topic related to either maths or physics, let me know and I'll try to cover it as well. Subscribe for more explanation videos like this. Thank you.